Okay. So, plan for today is to continue doing examples on the theorem I covered last time, Stokes Theorem. It turned out it didn't have much to know, so I thought, okay, I'll just go ahead and look at the homework assignment. And I found a few good examples there. Although I also found that the Stokes Theorem is 15.7, so it's the second to last homework assignment. It's not due until like the Monday of finals week. And there are 10 problems. And you can save yourself a lot of time by guessing if the answer is 0. and about half the time, I think you'll be right. But keep in mind, that will not serve you well on the test. So just a thought. That, I want to make sure that you can still do it. And then I've picked out some for which the answer is non-zero. There'll be one problem on the final out of over 15 problems in the final altogether, and one of them will be on Stokes Theorem. But there'll be various problems that deal with integrals over surfaces and curves for one thing or another. Okay, so as an example, we have the vector field F, that is xy, 2z, 3y. So these are our components, P, Q, and R. And what the problem asks for is to compute the line integral of the vector field F over the curve C, and the curve C is the intersection of the cylinder, x squared plus y squared equals 9, and the plane x plus z is equal to 5. So what that looks like here's your cylinder. And then you have a slanted plane cutting through it to give you, so this x plus z is equal to 5. That's a 5, not an s. So this right here, this intersection, is your curve C, this oval-like shape. But this closed curve clearly defines a surface S, which is just a portion of this plane. Okay. So for a problem like this, of course, you could just go parametric equations for this curve C and evaluate the line integral directly. But the point is, there's another way, and that is to use Stokes Theorem. And what Stokes Theorem says is that the line integral of f over the curve C is equal to the surface integral over S of the vector field given by the curl of F dot product with the normal vector. So this is the integral we're actually going to evaluate. So it's not parametric equations of C that we need. It is parametric equations from a surface S bounded by that curve. Okay. So for S, we can, since this is taken from a cylinder, it makes sense that we use something along the lines of polar coordinates for x and y, and then we can get z from the equation of the plane, since every point in the surface is contained within this plane. So let's find x is equal to u cosine v y is u sine v, and then z comes from the equation of a plane. So it would just be 5 minus x, which would be 5 minus u cosine v. Now, the other thing we need is limits on the parameters u and v, because those will be the limits of this integral that we'll eventually evaluate. So keep in mind that u and v are treated as polar coordinates. So u corresponds to r, and v corresponds to theta. And based on these equations here, that we're taking the intersection of this cylinder with that plane, what should the bounds on u and v be?
U should be from 0 to 3.
Yeah, 0 to 3, because 3 is the radius. We have x squared plus y squared equals r squared. 3 is the radius of the cylinder. So u goes from 0 to 3. And what about v?
0 to 2 pi.
Yeah, 0 to 2 pi. We're going all the way around. Okay. All right. So we have the limits for our surface integral. But now what we need the curl of f. And we also need the normal vector of a surface that comes from these parametric equations. Okay. Whoops. Okay. So now we can go ahead and take care of those things. What's my department head want? Okay. Okay. So first, the curl. So the curl of a vector field F, which in this case has components P, Q, and R. So that is a vector field with components Ry minus Qz, these are partial derivatives, Pz minus Rx, and then Qx minus Py. Now in this case, all right, so from the other board, P is xy. Let's have everything in one place. Q is 2z, and R is 3y. So, all right. So what are the components of this curl going to be? Yeah, 1 for the first component. dr dy is 3, dq dz is 2. Okay. Yeah, 0, because these don't depend on their respective variables at all. Yeah, minus x. Okay, so 1, 0, then minus x is the curl. Then the next thing we need is the normal vector. So we take our parametric equations. All right, so we need Ru cross Rv. So we need the parametric equations, derivatives of these parametric equations with respect to u and v. So what is our Ru? So it's xu, yu, zu is what? From these parametric equations over there. Mm-hmm. Yeah, minus cosine v. Okay, and then Rv will be the derivatives of all of these with respect to v. Anybody?
Theta q sine v.
Mm-hmm. Mm-hmm. cosine v. Okay. Now we need to take the where'd it go? Okay. Oh. Okay. So now we can take the cross product. Okay, so we have sine times u sine, so u sine squared v plus, because of a minus here, plus u cosine squared v, but cosine squared plus sine squared equals 1, so we get u. And then for the second component, we have u cosine v sine v minus u cosine v sine v. So everything cancels out and you get 0. And then for a third component, you get u cosine squared minus a minus, so plus u sine squared, so again we get u. So u, 0, u is the normal vector. Now since it's normal to the plane x plus z is z equal to 5, you can tell from this equation, this is something that you will have learned in Cal 3, that the normal vector, components you can read off the coefficients of x, y, and z. And so the coefficients would be 1, 0, 1. So equal components in the x and z directions, but the y component is 0. But the actual magnitude depends on what parametric equations you pick. Okay, so now we have all the information we need. So the integral over the surface S of curl F dot normal vector, the integral from 0 to 2 pi in V and 0 to 3 in U. A curl is 1, 0 minus x, but x is u cosine v. Dot product with the normal vector, u, 0, u, du, dv. Okay, so the set, well, essentially the setup is complete. We still have a dot product to do. But any questions about the setup? Right, so Stokes Theorem for a surface integral, curl of your vector field, normal vector, take your dot product. So now we multiply these components and add them up. And we have, okay, u, 0, and then minus u squared cosine v. So now you just go ahead and integrate from here. And now one thing that is good to keep in mind, if I break this up into a difference of two integrals, so u du dv minus 0 to 2 pi, 0 to 3, u squared cosine v du dv. Now the cosine v I can pull out to here. So just focusing on this second part, you have 0 to 2 pi cosine v dv, and then 0 to 3 of u squared du. So this is something, it's one of those little things that if you remember it, it can save you some time. If not, you can still work it out because, of course, you guys know how to integrate cosine, or you better by now. But the integral of sine or cosine of whatever variable you have over a full period, 0 to 2 pi, always turns out to be 0. Okay. So, because what would happen? What's the integral of cosine? What? That's a derivative. just plain old sine. But either way, then you plug in the limits 0 and 2 pi, and sine is 0 at both of those. So this part ends up not making any contribution whatsoever. So all you end up with is 2 pi, because there's no v dependence here. And then you can just finish that one off from there, and you end up with 9 pi as the final answer. This example is from page 144 and 145 in the notes. Okay. As we've seen in this class, where there's examples here, or certainly in the homework, lots of things turn out to be 0. So if you can remember certain things that tend to turn out to be 0, like this, one less thing to handle, with one less chance to make a mistake. Any questions on this one? All right. So you don't have any homework questions. The next homework's not due for a few days, but since we have time, I'll probably throw it out there. The next assignment's due on Monday night, so it'd be a good idea to bring some questions with you then. Okay, in the meantime, here's some more examples from an upcoming homework set on Stokes Theorem. Okay, this one I'm going to do first because actually the hardest part of this, well, for me anyway, was actually, once I'd worked out the answer, actually entering the answer. That MyLabs Plus made it a pain to do. So at least I can get you over that hump. So you need to pull up a problem here. Okay. So this is from a 15.7 homework, last problem, number 10. And it's a bit of a strange one. But yeah, if you're really, really pressed for time, just go through all the problems, enter 0, see if it takes it, and then go back and see which ones you still need. Okay. Now, so what we have is the surface S is enclosed by a disk. Actually, that's really suspect terminology in their part. It's really a circle. And the disk would be the interior. So S is the disk. So the circle C has these parametric equations. Okay, so the x component is cosine phi. Actually, you can write it like they do in the site. Cosine t. Next component, y component is sine t. And the z component is sine phi cosine t. Okay. Now, this is rather strange because with curves, we're accustomed to having a parameter t, but what's this phi doing in here? So t, as usual, goes for a circle, goes from 0 to 2 pi. And phi is a fixed angle. And it assumes some value between 0 and pi over 2. So it's not specified what its value is, you just know it's some value. You treat it as a constant. So that's what they mean when they say it's a fixed angle. Okay. So for purposes of differentiating, integrating, stuff like that, you treat it like it was any other constant. And what the problem asks for is find a circulation of the vector field F, which is given to be minus y, x, and 0 on the curve C of this strange circle that has a parameter. Now, the thing is, since your circle is described in terms of this unknown angle phi, your answer, the circulation of F, will depend on phi. Or maybe I should be saying phi. At this point in the semester, I really don't care. Okay. Now, so two technical hurdles. Okay, so for your MyLabs Plus headaches related to this problem, first of all, if a function comes up in your answer, like because you have a selection of math symbols that you can easily put in, like pi and square roots are used to handle things like that. But as far as it's like cosine or sine, etc., you just go ahead and type it in, and it'll recognize it. And then for this angle, that's going to be involved in your answer. So what you do is use for phi, use a keyboard shortcut. And that would be \v phi. Because there's actually two phi's. There's this one and this one. That's the one you want. So at the point when you're typing your answer, type in that, and it'll take it. Okay, so those are the technical issues. But now, what about actually doing the problem? Because what they ask you to do is use Stokes Theorem. That says, as done in the previous example, circulation of F is equal to the integral over the surface S of the curl dot product with the normal vector. But here's the problem. They give you the parametric equations of C, they don't give you parametric equations for S. Now you can get them from here, but I need to explain how. So first thing I want to point out is, how does this surface S and the curve C that bounds it, how does it actually behave? Because it depends on this angle phi. So I'm going to point out two extreme cases. If you let phi equal 0, then your circle turns out to be, well, cosine of 0 is 1, so we just get cosine t. And then you have sine t. And then sine of 0 is 0, so you end up getting 0 for the z component. So all you end up getting is a unit circle in the xy plane. Okay, so this is phi equals 0. Now, for the other extreme, pi is equal to pi over 2, then your circle becomes, well, cosine of pi over 2 is 0. So you get 0 for the x component, sine t. And then sine of pi over 2 is 1. So you get cosine t. So it looks like it's your unit circle again, except instead of being in the xy plane, it's in the yz plane. So what ends up happening is, and I'm not sure if I can make these pictures look any different because I'm on a two-dimensional blackboard, but so if you were looking down the x-axis, and therefore you're staring at the yz plane, you have a unit circle contained in that plane. So in other words, what the angle phi is doing is it's taking the circle and it's causing it to be at an angle, so it's tilted. So the angle is 0 here, pi over 2 here. So for intermediate values of phi, you have a unit circle that's slanted. So it starts out flat in the xy plane, and then it tilts up until it's going vertically when phi is pi over 2. Just to understand how this curve C and surface S are behaving for different phi's. But the real dilemma is you need parametric equations. So your surface S has these parametric equations. All you need to do is, you know that you can parameterize a unit circle by setting x is cosine t and y equals sine t, like was done here. But if you have a disk, so the circle and the interior filled in, how would you parameterize that? That's a surface now. So if I have the unit circle all filled in, I want the boundary and the interior, and I need x and y, parametric equations as functions of u and v. Well, what can we pick, as we've done in several examples?
U cosine V.
Yeah, u cosine v and u sine v. And u goes from 0 to the radius, which in this case is 1, and v goes from 0 to pi. So all you're doing is you're taking your parametric equations for your circle, which is x is cosine, y is sine, and you're slapping on a radial variable. That's all you need to do. They don't really explain it in a problem, which is why I'm telling you now. So x we can write as, we have a u cosine phi cosine v. So let's use u and v as usual. And then we have u sine v for y. And then z is u sine phi cosine v. And u goes from 0 to 1, v goes from 0 to 2 pi. So those are parametric equations you can use for the surface. And then what you can do is, like we've done in other examples, you find the curl of your vector field, you find the normal vector from your parametric equation, so you do RU, RV, and RU cross RV, and then you integrate with these bounds on u and v as your limits. And so aside from that, it'll work out like any other surface integral, so I'm not going to carry that out here to give away the answer. The only wrinkle is, because of this cosine phi and sine phi, that's going to give you constants that you have to pull out of your integral, and that'll be a lurking error in your final answer. Okay, so I want to make sure that this problem is reasonably doable before you jump into it.
Any questions?
Okay. Now, I have a couple others to look at from this same assignment. Okay. Okay, so this is from the same set. This is number 5. Okay. So the problem asked for is evaluate this. So we give you this surface integral of curl of f, which they write as del cross f, because that's how the curl is defined. So these two mean the same thing. I always write curl, but they're writing this. Dot product with the normal vector, where S is a disk enclosed by the curve C that has these given parametric equations that are rather strange. 2 cosine t, 2 sine t, and square root of 6 cosine t. All right, so it's a tilted circle of radius 2. Okay. And the vector field F is given to be x plus y, y plus z, z plus x. Okay. Let's see, any other information? Okay. And n is assumed to have upward orientation. But that would just lead to counterclockwise orientation for curve C, so nothing out of the ordinary there. But they tell you, as the theme of this section, to use Stokes Theorem, which means you're not actually going to evaluate that. You're actually going to evaluate the line integral. So this is Stokes Theorem going the other way. So Stokes Theorem problems are either asking for a surface integral or a line integral, and use Stokes Theorem to switch which integral you do. Because it can go either way to make the given integral easier. So we're just going to have this, okay. But this you can express as p dx plus q dy plus r dz, where these are the components of your vector field. So now you can treat this like any other line integral. Oh, sorry, oh, this is interesting. Okay, it's a good thing that I chose this problem because we didn't bother specifying the limits on t. You can kind of infer from the fact that it's supposed to be a closed curve that t goes from 0 to 2 pi, which it does. But it would have been nice if they had said that, so I'm telling you now. So you'd have the integral from 0 to 2 pi, and then you can fill in your parametric equations here for f. So you'd have, okay, so we have x plus y, so 2 cosine t plus 2 sine t, dx. So from your parametric equations, you have dx is a derivative of this, minus 2 sine t dt. dy is a derivative of this, 2 cosine t dt. And then dz is minus square root of 6 sine t dt. So now you can just fill in all of these pieces, x, y, z, and then dx, dy, and dz. So we have dx is minus 2 sine t plus q dy, so that's 2 sine t plus square root of 6 cosine t, dy plus r dz. So it's z plus x dz, which is minus square root of 6 sine t, all dt. Okay. So after you sort all that out, if you look at and simplify as much as you can, I want to point out the types of terms. So I'm not going to quibble with the constants here, but the kind of functions you need to integrate. You get a sine squared t. You have a cosine squared t. You have cosine t times sine t. Okay, those are the ones that come up. So here I can give you more time savers. Because we're integrating from 0 to 2 pi. So when you, I'll do sine squared, the integral for cosine squared is similar. So sine squared t, you rewrite that using a half angle formula. So that would be 1 minus cosine 2t over 2. And if it was cosine squared, same thing except you'd have a plus. But it turns out when you integrate the cosine 2t from 0 to 2 pi, you're going through 2 full periods. This part, the integral of that's going to turn out to be 0. This is how it always works out. And so you only have a 1/2 from 0 to 2 pi. So you get pi. So the integral of sine squared or cosine squared t from 0 to 2 pi, so again covering a full period, always turns out to be pi. This one, you can use as u substitution. Let u equal to sine t, and then du is cosine t dt. So you wind up with the integral of u du. So that's the situation. It's come up a few times for us, but you can handle it that way. Now, one thing I want to point out is I've given you shortcuts for integrals of just plain old sine or plain old cosine, and then also their squares from 0 to 2 pi. You get something different, like sine of 3x, or like from 0 to pi over 2 or something like that. Those time savers no longer apply. So don't try to apply them where they weren't meant to. I'll regret giving such time savers out. And these particular ones, they happen to come up pretty often. So use responsibly. Okay, so any questions about the setup of this one? Okay, so this is an example of going from surface integral to line integral. Okay. And, okay, I have a little time to discuss one more, at least the setup. So this is number 6 from the same assignment. Okay. So this goes the opposite direction of the previous one. So to evaluate the line integral of vector field F, using Stokes Theorem. So really you'll evaluate surface integral of a curl. And the particulars here, F is the vector field minus 9y minus z and x. And the C is a circle x squared plus y squared is equal to 15, sitting in the xy plane, so z equals 0. So therefore, the surface S is the disk, s squared plus y squared, is less than or equal to 15, and z equals 0. So, so the parametric equations, x is, like a broken record, x and y are u cosine v and sine v, and then z is going to be 0, but, okay, v, nothing special here, goes from 0 to 2 pi. What about u? What should the limits on u be? This one's a little different. What's the radius?
Square root of 15.
Yeah, square root of 15. So that's your upper limit on u, and then going starting from 0 as usual. Okay. So then what will happen is, since this is a disk situated in the xy plane, your normal vector should point straight up. So the x and y components will be 0. It's just a matter of what is the z component. So what will happen is you compute your RU, which would be cosine v, sine v, and 0. RV is minus u sine v, u cosine v, 0. So your normal vector, so when you, something to keep in mind, it could be a potential time saver. Because of just geometrically, you know the normal vector is going to be pointing straight up. It's going to be 0, 0 something. So in fact, you can conclude from that right away. Also, if the z component of your RU and RV are both 0, that means your x and y components of your normal are both going to be 0. It always happens that way. And then as for what's left, we have u cosine squared plus u sine squared. So that turns out to be your normal vector. And then the curl, in this case, because of you're differentiating these with respect to x, y, and z, and you get, so it works out pretty nicely actually. You get, in these numbers, you get 1, minus 1, and 9, but only this one actually matters, because you're going to take the dot product of your curl with your normal vector. So you have, okay, 0 to 2 pi in v, 0 to square root of 15 in u, and you have 1 minus 1, 9, dot product with 0, 0, u, du, dv. So your entire integrand just turns out to be 9u. So there's not much to integrate. But are there any questions about the setup? Wait. All right. Well, I'm done then. Just make sure to put your name on that before you leave. I'm making a mental note of who's here and, more importantly, who isn't.